As I get into more complicated assembly and integration with additional peripherals, such as SPI type of peripherals, one of the things I'm going to need to be able to do is to be able to do additional debugging. This Arduino up here has been handy at a slower speed to actually see what's on the bus and kind of decode it at a low level. And that's good for checking that ROM and RAM and things like that are actually communicating and working properly. But once I'm running at full speed and I want to somehow debug what's going on, that's not going to be sufficient. So what I have added to the system is an additional Arduino. It's just a Nano sitting here. And I'm communicating to it with SPI. And then SPI, of course, from the Nano is connecting to my computer through USB serial. And what you see on the screen is TerraTerm. It's just a terminal program. So this Nano is basically being read as far as serial communication is concerned from this TerraTerm. So I'm going to go ahead and turn on my system. I'm running it at full speed. So I have a 24 megahertz oscillator, which means that the processor is running at 6 megahertz in this demo. And so when I turn it on, you'll notice I get my normal prompt here. You'll also notice here on the screen for TerraTerm, it says initialization complete. That's just the Nano saying, okay, I'm ready to receive SPI communication. And I can write to that really just like any I/O device. So in my assembly, I can tell it to send a character to that, or I can write some assembly that says write a string to it, or whatever I want to do with it. For now, I've just simply said anytime I press a key on my keyboard, show me that on the TerraTerm. So if I come in here and I type in hello world and I press enter, you can see that this is working just fine. If I can type, of course. And there, when I press the shift key down, it actually passed that shift key, which in my Nano, I'm not doing any processing, so it's just displaying it as a question mark. But you can kind of see what I'm getting here. If I hit escape at this point, I still get my math coprocessor, and I still get this SPI communication working. And that's all coming from the same via that I'm controlling those with. So I now have two SPI devices. You can maybe see in the video I have a third one here. This is an SD card reader. I've not connected it yet. That'll be the next thing I do. But before I wanted to get into SD card communication, just because it is a bit more involved, I wanted something like what's on the screen. You know, something that I can print out to and say, you know, this is for SD card testing. Let me show you real quickly what I did to actually configure this up. Actually quite straightforward. Once it's all working, of course, it really looks pretty simple. So here I just have a Nano, nothing fancy about that. So just whatever they are nowadays, $3 Nano sitting here. And I have connected my MOSI, my clock, my S clock coming from this chip for the SPI. And then I also have my chip select. So I had to use an additional chip select pin. So if I go over to my schematic for a minute, what I've actually done is I've used chip select number 2. So this chip select 2 here is now this Nano device. And then I'll probably have chip select 3 be my SD card reader that's sitting beside it. So now I have three devices. This little LED, my Nano, and an SD card will be my first 3 devices. And they're kind of just increasing in complexity as they go. If I go look at the Nano code real quick, this is what the Nano code looks like. So if I scroll through this, you can see there's not terribly a lot to it, 100 lines of code or so. If I take a look at my code here, in the setup, this device, I need to set it up to be an SPI slave device. And so I need to have it listen to be a slave, and there's some things I do. First of all, I set up serial so that I can write to the computer USB port, and you can see I'm running 115K times 3, so you can multiply that out. But that's the speed that I found I can run this at consistently well. And you'll see that when I come over here and I configure my serial port, I match that same value, so 345, 600. Seems like if I go faster, the Nano just can't quite keep up with it. And then I set a few register values on the Nano. One is to enable SPI with interrupt support, and I clear out, or I basically, actually this status register I don't even need. I set up a register here that I set some settings that say go ahead and enable SPI and enable interrupts with that SPI. I set my pin modes on the 4 pins that I'm going to be using, so MISO, MOSI, my clock, and then my cable select, or what's referred to as SS here. Another way of doing this without this way I've done it here on line 27, you can use this SPI attach interrupt. My understanding is that is a less preferred way of doing it. So I'm just using this up here. And if anybody has any opinions on that, let me know. And then once that gets initialized, I just simply print out to the USB terminal that initialization is complete. And then I have an interrupt, so that Nano just sits there, and once it receives data, I read the byte of data that it receives from SPI. So that would be coming from my 286 through the VIA to the Nano. And I then track what packet number. So if this was the first packet number, I'm going to just capture it as a command. And if it's the second, the sequential packet number that comes after that, I'm going to process it as a byte of data that I'm going to use. And I'm just going to basically set up a series of commands. So the first command that I'm going to support is command 0, which is just do a reset of the Nano. Command 1 will be a print char, then I've got a print hex and a print binary. For now, the only one I've implemented is print char. And so I catch those when the interrupt happens, and after I've grabbed both the command and the data that goes with it, then I do something about processing it. Now, just a quick note, this is just for testing. When I get this done, you don't want to do any serial prints or any extended processing inside of the interrupt. You want to keep that as short as possible. So I'll end up showing or throwing some of this into some sort of an array of commands that are queued up to be processed, which I'll then process way at the bottom in the loop. But for now, this is sufficient for testing. And then in the process command, I come in here and I simply say if the data byte was a 27, well, first of all, was it a print char come into here, into this case? If it was a hex 16 or a binary, come down to these things. But if it's a print char, and this is the only one I've tested so far, these other two I think should work, but I need to test those. But I have a command print char. If it was an escape, do something different with that. I need more filtering in here, but that was the first one I started to lay out. Otherwise, go ahead and convert that byte, whatever the number is, to a character and print it out through the serial. And then I've got procedures that do a print hex and a print 8 bits at a time type of thing. So that's all there is to the Nano code. And if I flip over then to the assembly code, previously I had the write byte and read byte for SPI, and I used that with this little LED display. I have now added in addition to the send LED command, it was send LCD command in my last video. I corrected that, so it's send LED command. But I now have a send nano serial command. And in that, I then basically go through the appropriate SPI calls to send the command number, which is command 1, and then also include the data that goes with that. So what character, what's the ASCII value of what you want to print on the Nano serial output. Quick heads up, there are 4 different modes of SPI. I am using the most common mode, often referred to as mode 0. And so in this just means certain things. For example, when I start out with writing my SPI, the initial state, I need to keep the clock low. And what you're going to see what this code does is it basically says, okay, I want to move into the lower A register, and then I'm going to write that out to a variable that I've called SPI state. And in that, I'm going to write down a 1 for a position of CS1. That's my, the first device, which would have been this LED numeric 8-character 7-segment. CS2, and maybe spacing wise, I'll go like this. So I'm saying, okay, CS1, CS3, 4, 5, all of those I want to be high. And I want CS2 not to be included, which means it will be low. And I also want MOSI to be high. And so that's how I'm going to start writing, is by dropping my chip select for CS2. And CS2 is, again, for the Nano. Before, in my previous code, I only had one chip select to worry about, which was the chip select for this LED display. But now that I'm supporting multiple, I need to make sure that I tell all the ones I'm not using to have a high value for their chip select. Only one can be low at a time. And you'll see that I went into my corresponding send LED command and I did the same thing. So I am pulling all of them up except for one, which one is for the LED 8-character display. So then I basically continue, and I am going to go out and I'm going to write the high byte, and I'm going to write a low byte basically out to SPI, to whatever device, and in this case of the Nano. And again, I'll post this if you want to peruse through the current state of this. It's still a work in process, so I doubt it's perfect by any means. But where that gets called is now where I handle my interrupt for my keyboard. So I need to go find my interrupt for my keyboard, which is my keyboard ISR. So let me find that here. And in that, if it ends up being an ASCII key that's pressed, I'm going to go ahead and convert that ASCII or from the scan code of the keyboard to an ASCII value. This print char prints it up to this LCD here. And then I move into the upper register of the A register. A 1. 1 is a command that I'm going to send to the Nano, which is print char. So I'm saying print char, whatever's in the lower part of that A register, which is already in there, so I don't have to do anything further. And then I just say call this. So anytime I want to send a character to my Nano, all I have to do is move a 1 into the AH. And if my AL, my lower half of my A register, already has the ASCII value in it, I can just call this here, and that will then print it out. I'll make a routine that will print out entire strings. For now, I'm just doing a print character, and as I press a key, that prints out. Maybe one other thing I'll point out, as far as the code, that's about it for code. So the code is pretty straightforward. I did have to do a little bit of tweaking with it, though, and just trial and error in making sure I understood where I needed to adjust some of these signals. Like at what point did I need to make sure I had, for example, I was coming in with clock high to start, and that was putting me into a different mode of SPI instead of mode 0. And I did also adjust this write byte. So when I go out to the write byte, I did put a little bit more logic in there that had to pay attention to the SPI state. In other words, what were all of those chip selects? How should they be set for this specific call? And there's only one of them I'm pulling low. The others have to stay high. So I have to remember that. And then when I go toggle the MOSI, which is the actual value that's being sent, and the clock, I then am going to use this a complementary, basically invert MOSI, and also invert the clock. And this is how I'm flipping MOSI up and down and clock up and down within this code now, keeping all of this state intact as I go. And that's all working quite well at this point. The thing that I had to do besides, just really looking at the code, I really had to get in here to this SPI debugger I'm using right here. And I'll just show you what this looks like at this point. The system's still running, so if I press a key, let's just say hit an R, I want to be able to capture that data on here. And I'm going to go ahead and have it scan, and I'm scanning pretty fast rate now, faster than I was before in the first video. And so again, I'm running full speed on the system, so 6 megahertz, and I'm scanning at 1 megahertz, which is, I think, sufficient. But I'm going to go ahead and hit a key, and then I'm going to hit stop, and then I'm going to zoom into that blip that you see there. And that is the data that is giving me that command 1 and a hex 72. So the hex 72, that must be a lower R if that's the key that I hit. And then I can see that what did I also get for a response? I got a 1 down here. I don't think I'm doing anything on the Arduino for this specific code to send back any MISO data, so just disregard everything for MISO. I'm not doing anything with that. But if I look at the clock, I can see I have my nice 1, 2, 3, 4, 5, 6, 7, 8, and another 8. Those are looking good. I can see that I drop my select low, and I have to have my clock low before I drop my select low. And so clock low, then select low, then I work my way through the rising edge here is then where it will read the MOSI. So in this case, it's going to read a 0, 0, 0, 0, 0, 0, 0, 1. And then it's going to get over to this one and kind of repeat the same type of thing. So it's going to have a 0, a 1, a 1, a 1, 0, 1, or 0, 0, 1, 0. And then at the end of all of that, and actually I did find that with the bar, the LED numeric output here, this 8-character LED, I didn't have to change the select in the middle of each byte, but I find that with the Nano I do. So basically I'm going to send a byte and I'm going to basically pull the chip select high at the end of that. So drop it low, get 1 byte of data sent, bring it up, drop it low, get the next byte of data, and bring it up and continue. And that's working great. And then, like I said, I think this little 8-character display is a little bit more lenient, where I didn't have this middle bringing the chip select high and back low again. I just left it low the entire duration, and it was perfectly fine with it. And that is part of the challenge with SPI. I think different devices have different compatibility and modes that they'll support and levels of tolerance of how clean or sloppy your SPI signals look. Something else I found helpful in this tool, there's a protocol tool. So I can look at it Logic Analyzer like I was just showing, but I can also go to protocol and I can tell it to start receiving. And now when I hit a key, it just shows me the data it received. So it says I got a 1 and a 71. And if it receives the wrong number of bits of data, basically, if there's not enough clocks or too many clocks, something's not lining up with the chip select, it'll tell me, it'll give me little warnings here that says received 3 extra pieces of data. And so when I was first coming into this, I was getting a bunch of that. It was just, I was catching problems, but now I can come in and just, run through this quite quickly, and it's coming out very clean. It's saying, okay, command 1, 71, command 1, 74, 1, 68, etc. And that is all working just fine. And you will see that, back over here, this moves as fast as I can move. My bad typing and all, but and as fast as I'm going through that, you can see it in the background capturing that data. You can see, keep in mind that as I hit a key here, first of all, I have to capture that key up here in this circuit. I have to then raise an interrupt back to my processor from the PPI number 2. Processor then has to process and do something with that, and then it's got to turn around and come down to the VIA, and then the VIA needs to write the SPI data to the Nano. The Nano then says, okay, what do you actually want to do with it? You want to output it to the serial output. Now send it to the computer, which then is displaying it in this terminal. So every one of these keystrokes is going through quite a few steps, all the way from there to over here to back and then back out. But you can see that it's plenty fast. So I have no concern with this for a debugging tool. I think it's going to come in pretty handy. So the next thing I'm going to get into then is I think I'm going to try to get this SD card working. And what I'm kind of thinking I might try to do with the SD card is possibly load different BIOS images off of it on the fly. So I might try to configure the system so that I'll have still two primary BIOS chips here, but they might just have just enough logic to maybe prompt me which BIOS image do I want to load. And then when I choose 1, 2, or 3, or whatever the choices are, it would then go out and pull that BIOS data off the SD card and put it into RAM. And that means I'm going to shrink my ROM space maybe further. I don't know. We'll see. Right now I have it at 256K, but I can maybe just take the top, I don't know what I'll need, 40K for this basic loading, and then maybe I can go fetch 200K of stuff and load it into RAM in that same space. So I could actually shrink my ROM space further, give myself some additional RAM space, and then load this ROM data from the SD card into that additional RAM. So kind of doing a shadow ROM type of concept, but my source would not be coming from ROMs, it'd be coming from an SD card, which I think will work just fine. And I won't know until I get there, so I am going to work on that. Step 1, though, is going to be, can I simply read SD card data from here and then maybe display it to this new debug output that I just got done working on. If you've got any ideas on that, thoughts or suggestions, feel free to drop me a note. But thanks for watching.